Let's start with the new chapter 4, which is an extension of what we did in chapter 3. It is going to be supervised learning, but more on the ML side. So we'll discuss mostly about decision trees in depth. One of the most oldest and popular techniques or algorithms in supervised learning, decision trees. We'll talk about decision trees, then we'll talk about k nearest neighbors, and then we'll get into a little bit of bagging and boosting, which is nothing but some sort of ensemble techniques. And then we will also talk about neural networks. We've been talking about neural networks almost everywhere, but we'll talk about neural networks, transformers, a little bit about that. But this is what we are going to talk about in this video. So let's start with decision tree. Decision tree, as the name suggests, it's like a tree-like structure. These are called like your white box models, because your unlike the complex forms of algorithms, these models are more easy to interpret. Let's suppose you're trying to find the default probability of people, okay, and you want to say that I want to have features like your credit score, maybe your salary, and maybe what else it can be, maybe your asset value. Okay, so a decision tree may look like this. It will have a node called as, let's suppose it says credit score is more than probably say 700. Okay, so it will have two things, one is yes and one is no. So there is a there is a condition that you check, and based on the condition you check more conditions. So it looks like a tree, right? So again you say, okay, this is yes or no. Then you say, if income is more than say 200,000. Okay, if yes, you can say that my credit score is high. If it is, this is yes, this is no. Okay, if it is no, you check the asset value, and if asset value is more than, let's suppose, 1 million, if it is yes, credit score is high. Okay, if it is no, your credit score is medium. And then you'll have some conditions on this side of the tree as well. So all the leaf nodes will have some value of credit score classified. So this is how a decision tree is seen. And if you look at it, it is it's primarily used for classification. However, there is a form of decision tree that is called as CART, classification and regression trees, where you can also use decision trees for regression, although it is very rare, because see, at the end of the day, the leaf nodes have to be a finite set. And if it is a finite set, theoretically it is not continuous, right? It cannot be continuous. It's still some discrete values. So if it is say credit worthiness of an individual, you can have 100 leaf nodes, right from 1% to say 100%, but then again, it's still non-continuous, because you may still want to further put somebody as say 40.2% to 40.3%. So all of that fidelity is lost. So but anyways, theoretically, if GARP asks you whether decision trees can be used for regression or for classification, yes, they can be used for both regression and classification, and the ones that are used for regression are called as CART trees. Now even for classification, we noticed that there can be some values, feature values, which are continuous. For example, we saw that what is the income of an individual, right? So income of an individual can take any value, probably 30k to a million or more, or whatever it is, right? So in this particular case, you have to find out some regions of this parameter, where you can say that, okay, if income is more than say 100k, or income is it has to be within say 50k and 100k, then there can be less than 50k, more than 100k, between 50k and 100k. So how do you find these regions of interest in case of of a tree? Is that, again, you do some kind of a root mean square, and then you find out, let's suppose there is a let's suppose this is my a space where, let's suppose this is my age, and this is your weight, or the distance that you can run, etc., etc., and then you can find some points here, some points here, some points here, and some points here. So if you want to break this into say some regions of interest, that this particular region can be one types of region, etc. So you find out the difference between yi and y bar. So y bar is the average for that particular region, and then square it, and then you'd find it for all the regions from say 1 to r, and then you you do it for all possibilities. Okay, so that's how you generally find out the partitions in a continuous variables. It is not possible to do it for every possible set of permutation combinations like this, so we generally go top down. So when you say top down, we think that everything is a single region, and then we break it into 2 partitions, and then 3 partitions, and 4 partitions, so as to find out the most optimized place where the tree can be broken down for a particular continuous variable. Okay, so that's how the partitions are done for a variable which has continuous values. I think we will get into a very important concept, which is let's suppose you have a kind of a list of values. Okay, let's suppose it's a credit worthiness of an individual, or the credibility of an individual, which is either yes or it is no. And then you have some values like your credit score, then your income, and then your asset value. Okay, there'll be some, and we have already, for all your continuous variables, we have already partitioned them into some portions, that if credit score is more than 700, it is category A. If it is let's suppose between less than 500, it is C. Between the two, it is B. If it is more than 700, it is A. Let's suppose we have already done that kind of a partition, and we put some kind of values here, and then we have this table. So now how do you decide that based on the data that you have, a labeled data, a supervised data that you have, how do you find out which of these 3 nodes should come first, whether your credit score should come first or your income should come first? So there are a couple of methods to do that. Actually, the method is one, but the matrices can be different. See, you need to find out the purity of the tree. Okay, purity of the tree, or you can also find out the if you look at it from the other way around, you can also need to find out the noise in the tree. So for example, if you look at this tree right here, there are 2 yes and 2 no. So this is the most impure form of a tree, where 50% of their cases are credit worthy and 50% of them are not credit worthy. So there are a couple of matrices that you should know. One is called as entropy, and these matrices can help you to find the purity of the tree, and one is called the Gini index. There are more as well, like your information gain, etc., etc., or there are variants of Gini index, but let's say that the entropy of a tree is p log p to the base 2 for all classes, and Gini is slightly simpler, and there is a negative sign because log 2 base 2 could become negative. It is 1 minus p square. Okay, so these are the two matrices, or these are the two KPIs that you need to calculate to find out the purity of the tree. So in this particular case, so this is log 2 base 2, unlike log 2 base n or log 2 base 10. So this is difficult to compute. So let's go ahead with this. So in our case, it is going to be for this particular case 1 minus. So what is the probability of positive class? It's 1 by 2 square, and of the negative class is 1 by 2 square, right? So it becomes 1 minus 1 by 4 plus 1 by 4, which is nothing minus 1 by 2 and 1 by 2. Okay, so the Gini index of your tree is 1 by 2. So now you have to, once you know the Gini index of the entire tree, you need to take scenarios. What happens to the Gini index if we use probably feature 1 as your root node, if we use feature 2 as your root node, and whatever higher the purity of the tree or lowers the noise of the tree needs to be calculated. I don't want to get into the calculations etc. right now, because if I take a working example, it will take me, not for me, for anybody, it will take a lot of time, like 10-15 minutes. See, mathematically it is not hard to compute. And then I'll have to take some real values here, but let's say that this is A and this is B. Okay, so there are 3 values of A and 1 value of B. So if I use the credit score as my tree, whether it is A or B, let me just try to do a small mini example. So credit score, if I say if it is A or it is B, on this side you see, you find yes, yes and no, right? So there are 3 values here, which is yes, yes and no, and here it is only 1 value, which is no. So what happens to the purity of the tree is that this anyway is 100% one class itself, but here it is 2 of the 3 is of one class and 1 of them is of another class. So in this particular case, if I have to find the Gini index of this node, it is going to be 1 minus 1 square, right, plus 0 square, which is nothing but 1 minus 1, which is equal to 0, right? But if I have to find it here, it is 2 upon 3 square plus 1 upon 3 square, and I do 1 minus. So 2 by 3 is because there are, out of 3 values, 2 are yes and 1 is no. So it becomes 4 upon 9, and this becomes 1 upon 9, and eventually this becomes 5 upon 9, and once you do 1 minus 5 upon 9, it becomes 4 upon 9. Okay, now the 4 upon 9 is the Gini of this tree, and the Gini of this tree is actually 0, but since the proportion of the proportion of the tree on this side and this side is like 3:1 or 75% and 1% 25%, you find the Gini of the tree as 75% of 4 by 9, and then you add 25% of 0. So this gives you the Gini of the tree. So similarly, you find out what happens in case you take income, in case you take asset value, and the one that gives you the most lower Gini or better increment is the one that you are looking for. So in this case, you can also find a variable called as information gain, which is what is the gain that you are getting. So let's suppose your when your unsplit tree was 1/2, and if you split on the basis of say credit score, it becomes probably say whatever it is. Let's suppose it becomes let's suppose it is 1/2 only. So when you subtract the 2, you get 0, which means that there is 0 in information gain. If it is 1/2 minus, let's suppose this gives you probably 8/9 or 8/10 or that kind of a stuff, then that means that this is a high information gain, right? So depending upon what you get as the value of Gini index for particular nodes, you can find the information gain, and based on that you can choose which node to select. You will find a lot of videos on the internet, and on the GARP book will contain 1 or 2 examples, but this is something that is very 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 implicit to all any algorithm or any video that you'll see. Hence I'm not spending a lot of time on this, and this is easily available everywhere. And I want to spend more of my time on GARP related things and things that you may not find at other places, rather than talking about these things. Okay, so next there is a small reading on pruning. So what happens that sometimes if your features are way too many, okay, if your features are way too many, you may not want to create a tree with all these features. So if you create a tree with all these features, it may also end up overfitting. We spoke about overfitting earlier, but it is like trying to model everything together in such a way that it also tries to model the noise that is present in data. So if you put everything together, it can create it can also model your noise into it, so you don't want to use all your features. Plus it is also slightly difficult to interpret. Okay, so for a human mind, if you give them so many features that okay, these are all the 100 features and this is how a tree looks like, which is going to be huge tree with hundreds of nodes, a human mind may not be able to process it. So that's why it is always advised to keep the length of the tree limited. So if there are multiple methods to do it, one method is to prune the tree. So you create the tree and then you start cutting it at some value where you find that either in terms of Gini index or either in terms of entropy, when you see that there is not much value in splitting this further from this node, you prune the tree from there. Okay, so that's when you build the entire tree and then you cut the tree. And the other option is while you are building the tree itself, at that point of time you restrict the length of the tree. So both of these approaches is going to give you the same thing. It's going to give you a smaller tree which is more interpretable and which does not overfit. Okay, so this is how a decision tree works, and now we should get on to, you try more questions around decision trees, you get into problems, you email me, and then I can either put up a new video on a working example, or I can send you some videos on the YouTube which will help you understand how this entire calculation works. So let's now talk about some of these ensemble techniques, which are generally divided into two parts. One is called as bagging and the other one is called as boosting. While these techniques are independent of whether you use a decision tree or any other algorithm. But while we generally take these kinds of sessions, we always talk about these techniques after decision trees, so that if we have to explain to you about these techniques, uh, we can take the working example of a decision tree and tell you how a decision tree can be put into action using bagging as a ensemble techniques or boosting as an ensemble technique. And there is one more which is called as a random forest, which is proprietary to a decision tree only. So these are the three ensemble techniques that just to give an analogy, one more analogy, what I would say is, let's suppose somebody is not feeling well and he wants to go to, say, a doctor or some kind of a medical treatment. So in that case, he will not just go to, in order to make sure that he is getting the right consultants for his treatment, instead of going to one doctor, he can go to, say, multiple doctors. Okay. And more the better, but sometimes more doctors can create more confusion. But anyway, having said that, and based on whatever majority of these doctors tell in common, he can take next action. Okay, so similarly, in case of a classifier, or even in case of regression, it is a good idea to take multiple models and then you combine them together and you ensemble them, and then you take the final decision. Okay, so that's the entire philosophy of ensemble techniques. And as I said, there are three things: bagging, boosting, and random forest. So let's start with bagging first, which seems to be the most easiest of the three. Now, what happens in case of bagging? You create multiple classifiers. Okay, and you train multiple classifiers on a subset of data. Okay, so let's suppose you have, say, 10,000 records. So instead of taking all 10,000 records, you take 1,000 records, and then you create a classifier, let's suppose CI. And then there can be two methods. One is you replace your tokens that you have already taken, or maybe not the tokens, the data set that you have already consumed, you replace, and you create another classifier, in which case there is a probability that some of the samples may get repeated. And then there is a possibility that you do this without replacement, in which case after 10 iterations, so C1 to C10, you will exhaust all the data set. So you can take either of them. The one where you do with replacement is called bootstrap aggregation, and where you do not where you do not replace is called pasting. But anyway, having said that, you create a set of classifiers, and you can do a majority vote. Okay, so whatever is your C1 to Cn, if it is a classifier, you do a majority vote. In case it is a regression, you can take some kind of a statistical mean or whatever you want to do. Okay, so that's the simplest method, which is called as bagging. Let's move on to the second one. Let's talk about random forest. So random forest, is a collection of decision trees. Now in this case, we just don't split on data, we also split on the number of features. So let's suppose you have feature 1, feature 2, feature 3, and so on and so forth. Now there is what happens in most of the cases is, let's suppose if there is a correlation between features, or some of the features are very, very less important, sometimes they tend to be ignored, and the value that they can bring onto the table can sometimes be we can ignore that, because of which our accuracy may not go beyond a certain number. So in case of random forest, you also create, these trees on a subset of features, and these are randomly selected most of the times. But obviously, if there is a feature that is very, very important, anyway, it is going to come on the top, and then it will factor in more and more. And then you also trim this to a particular level. And once you do these two things, you create a collection of all those decision trees, and then you can do aggregation of all of those things to get the final decision. So that's on the random forest. The third one is called boosting, which is also one of the more mathematically complex methods to make sure that your classifiers are a chain of classifiers are trained. So when I say a chain of classifier, in this case, if you are creating a classifier, let's suppose I+1, it needs to be proportional to the wrong predictions of classifier Ci. Okay, so what I'm saying is, let's suppose you start with, say, classifier 1, and you run this on some kind of a test data, and then there are a couple of samples that are misclassified. So these samples take more priority in second classifier, and so on and so forth. So it has there is some mathematical nuance that happens in case of this method of boosting, and I'm not going to get into the details of those mathematical nuances because all of that is not needed for GARP. But then there are some algorithms called as, say, XGBoost, which is a very, very powerful algorithm. Before the advent of neural networks, XGBoost was one of the most powerful algorithms which used to help a lot in accuracy. And then there can be a couple of more. Let me see, there is a AdaBoost also. Okay, so there is a AdaBoost, which is relatively simplified version, but these are some of these boosting techniques. Let's not and I think let's take a pause here with respect to ensemble methods, because principally you need to understand what ensemble methods are and what they can potentially do to make your predictions better and better. The next reading is on k nearest neighbors. Okay, so this is also some kind of a lazy method. So when I say lazy method, there are classifiers which run on a set of training samples, and when it runs on a set of training samples, it gives you some kind of a mathematical equation. And when you actually get your new data, you run that through this equation and you get the output. Okay, so this is something that is not a kind of a lazy classifier. It's a pre-compiled kind of a classifier. In case of k nearest neighbors, why we call this as a lazy classifier is that you have let me put it on an XY axis. Let's suppose there are 2, and these are some of your data points. Okay, now if these are your data points and you find the new data point that you want to probably, say, classify, or even if it's a regression, is here, you find out for a value of k, let's suppose you take the value of k as 5, you find out what are the 5 nearest data elements which are close to the one that you want to classify. So 1, 2, 3, 4, probably this is the 5th one. So you find out these 5, and since you need to do this every time you get a new data element, you cannot just pre-compile into a math equation. That's why it's called as a lazy classifier, because it is actually going through most of the data points at runtime and then find these k nearest points. Now why do we do k equal to 5 is generally we do odd number so that we don't get into a situation where if it is a binary kind of a classification, you have equal number for say x equal to 0 and x equal to 1. So if you put in an even number and you get 2 and 2, it becomes difficult to break that kind of a tie. So we generally take 5, 7, mostly 5 or 7, and based on what these values are, and if it's a regression, you can take the average. We find out the final classified class. So that's the k nearest neighbor. There are more nuances to k nearest neighbor on how do we find the value of k, etc., etc. We'll see if all that is required. I don't think it is required right now for this reading as a part of chapter 2. but but then there are methods to find how to find k. Okay, so how to find k, and then let's suppose this is your k and this is your quality or something like that, and then we find out that this is a kind of a curve. So we find that there is some kind of a point where it kinds of makes an elbow, and at that elbow point we see if the value of k is say 5 or so. That's how we find the value of k. How do we find, it was very easy for us that in a two-dimensional space we can do this kind of a visually we find out this is how these are aligned. But how do we find the distance metric? So that is also something that can depend upon case to case basis. Distance can be Euclidean distance, it can be Manhattan distance, or some other kind of distance measures which we already spoke. But this is how a k nearest neighbor algorithm is designed. So just an overview, because right now we are just glancing these methods or these classifiers, and the intent of GARP is not to mathematically probe you on how do we do all of these things, what is the math behind it, etc., etc. But in case in further readings, if there is some more details that we need to dig into, we can do that. Okay, the next one is something which is also very, very complex, but I'll give you a brief overview. I'll try to be as crisp and as concise and as brief as possible without confusing you. It's called the SVM, very, very popular. It's called the support vector machine. And again, before the advent of neural networks, this was also a kind of a very, very strong method. So let's take an ideal case first. Let's suppose there are some and it's a two-dimensional feature space. Let's just say that these are your one kind of classifier, one kind of objects, and these are your other kind of objects. Now you need to find a partition in between, or some kind of a straight line in between, which makes sure that the class 0 is on this side and class 1 is on this side. Let's just assume for simplicity it's just a binary kind of a classification. Now in this particular case, how can we maximize the distance between this space, this side, the first side and the second side? Okay, so there are calculations with respect to extraction of eigenvalues and eigenvectors, which helps you to extract all of this, but let's keep that aside for now. See, the intent is that you need to find out the instances which are closest to the boundary line, and these instances, and these are the questions that GARP may ask you, which are like these two instances on the class 0 side and these two instances on the class 1 side. These are called as support vectors, because they will help you, these all of them are called as support vectors. because they will help you to create this kind of a demarcation. And if you create a line from both these support vectors, you get this kind of a margin. Okay, and then you find a line in between which maximizes this margin, and it is going to be only single line that goes in between them. So these are called the support vector. This is called the margin, and this is the demarcation line that separates both of them. So this is what a support vector machine is. But I was talking about an ideal scenario. So ideal scenario may not always happen. So there are times when your instances will overlap, and in that case you can create some kind of a penalty for instances which overlap, so that you can still find out support vectors, and it might not be as clean as this is right now. The other option is to create some kind of a kernel function. Okay, so what a kernel function will do is that it is going to be a function on the top of your data points di, which can project it into some kind of another space where probably your finding support vectors and finding kind of a demarcation line in between is much more easier. Okay, so that's how it is mathematically. Just to put things in perspective, is there anything on the Garth has given mathematically how this is classified? No, I don't think so, but this is how support vector machine works. Okay, let's move to the next reading. So we can talk about each of these methods at length for hours and hours, but that's not the intent. The intent is to make you aware on a high level what these methods are. Hence, I'm not getting into too much of details. Otherwise, we can keep on and on. The next one is neural networks. Now, what happens in neural networks? Neural networks are a set of independent units called as perceptrons, which are arranged in layers. Okay, and there are multiple layers. The first layer is called your input layer. The last layer is called your output layer, and the ones in between are called your hidden layers. Generally, let's suppose it is for say some kind of a visual input or some kind of a imagery. The input layer is proportional to your dimensions of your input. So when I say dimensions of your input, if it is an image, let's suppose it's a 10 by 10 image, and we put 1 pixel each, and let's suppose a grayscale image 0 to 255, we will have 100 neurons here. If it is text, and let's suppose we are processing word by word, and each word is say 1 by 300 kind of a vector, then there will be 300 neurons here. Output depends upon what is it that you are trying to do at the end of the day. If it is a image, as I said, 10 on 10, and let's suppose we are trying to solve the classical problem of 0 to 9. There are images between 0 to 9, and you're trying to find out what is the image. So in that case, there will be 10 neurons here, for one for each digit. Now these neurons are connected with each other, fully connected, partially connected, but let's assume they are fully connected. So that's how all of these layers are connected with each other, and they will have, so for every connection, let's suppose we are talking about this particular neuron itself, so it will have how will this particular neuron consume all the information from all the connections that it is being fed into. So there is going to be a weight for each of these connections. So there is going to be Wi, and the data that comes with it, you add all of it, and then you add, say, your W naught, which is the bias. So that's going to be your kind of your scalar output. And since you don't, otherwise, if we don't process this scalar output, it is just going to be a linear combination of all the input weights, and at the end of that, it's going to become a linear classifier. So in order to make this more powerful and more non-linear, we need to pass this through a function, and that function is called as an activation function. I'll talk about this activation function in a while, but you pass this entire thing into an activation function so that your output can range, say it can be between 0, 1, or it can be between -1 and 1, etc., etc. So it depends upon what activation function you are choosing. It is going to bound the output of your final calculated value, and it goes on and on and on and on, and eventually it reaches here. And in the last layer, your activation function, instead of this, it can be, say, some kind of a softmax, which essentially means that whosoever gives the largest value is going to be fired. So if it is a binary kind of a classifier and this output is larger than this, then this is our final output. So that's how a neural network fundamentally works. That's the kind of a very, very high level of functioning of a neural network. And all your higher order neural networks, whether they are your CNNs or RNNs, are fundamentally, this is a neural network that goes behind all of them. Now let's talk about some of these activation functions, and this is something that came in our exam also when I was writing this GARP. So what kind of activation functions can be there? The first one is the logistic activation function, which is 1 upon 1 plus e to the power of, let's suppose, minus y, and this y is whatever we have calculated. So let me say this is y. Okay, so this is a logistic activation function. If I have to plot this on a graph, this is how it is going to be plotted. Okay, so this is 0, this is 1, eventually it is going to touch 1, and this is also eventually it's going to touch 0. Okay, so that's the activation function called as logistic activation function. Now the problem with this function is that it is not zero balanced on y-axis. So sometimes you use a tan h function, which is e to the power of 2y minus 1 upon e to the power of 2y plus 1. Just let me double check if I'm right or wrong. Okay, and that's fine. And the advantage of using a tan h is that your function is going to become more like this, which is go to the 0, but it is going to become more like this, and it can range from, say, +1 to -1. Okay, so that's on the tan h side. And then there are activation function called as ReLU. Okay, so in case of ReLU, what happens that if your value is say less than 0, let's suppose this is your y or z or whatever you want to call it, it becomes 0. If it becomes more than 0, then it becomes whatever is the value of your y. Okay, so this is your y, this is your output. So this is some kind of a 45-degree angle. So if it is more than 0, then your output is, for more than 0, it is same as your y, and if it is less than 0, it is 0. Okay, so that's ReLU, and then a kind of a more a different variant of ReLU is called as leaky ReLU, in which we create some kind of a leakage factor, and if it is a negative value, we do some kind of a, it's not 45 degrees, but it is going to be like this. So this is called as a leaky ReLU. So these are some of your activation functions that we can use in case of neural networks. There can be you can get some kind of questions with graph displayed and asking that what kind of a activation function it is. There is one more fundamentally important thing in neural networks, which is called as back propagation. So what happens when you train your neural network? Training a neural network is very compute intensive job. So you pass all of these values. Let's suppose we want to take this kind of a digit classifier, and then you pass this on from here, and then you reach your final layer. And when you reach your final layer, not always, since we will start probably with say random weights, you will not always get what you would want from your classifier. So let's suppose it goes to the final layer, and it let's suppose your final layer has 0 to say 9 neurons. Now let's suppose you were putting a 5 number here, then ideally your this 5 should be 1, and all of these should be 0 values. Okay, 1 2 3 4 5 6 7 8 and 9. This is what you were expecting. But since you started with random initialization, you may not get these kinds of values. Let's suppose you get some other values. Let's suppose you get some 0.3 here, 0.2 here, maybe 0, and then 0.0 something, maybe very close to 0 values, and then you get, let's suppose, 0.2 here, and then 0.2 here, and some more values. Let's suppose we kind of balance them so that the total is 1, like this. So now we want to tell this neural network that this should go to 0, this should go to 1, and so this is something that we were expecting. Now based on what kind of path it has followed to get these values, the difference of these values is something that we need to propagate backwards and update the weights. And we do this n number of times, say 1,000,000 times, and eventually we will get what we are expecting. So this is not as simple as I have been telling you that this is just find the differential and then go back. There is a lot of complex math that goes behind it, how back propagation actually works, and this is one of the discoveries, very important discoveries that led to the evolution of neural networks and made them so powerful. And this is something that we do every day, even in the more complex CNN, RNNs, transformers, etc. All of this becomes the backbone of how weight training is done. So that's the back propagation. Fundamentally, I thought I'll just tell you conceptually what back propagation is all about. Okay, so let me go to the next reading, which is more about your okay. So there are 2 more things that we need to cover as a part of this chapter, and then we'll move on to the next chapter. The next reading is on other neural networks, which is CNNs, and a little bit on RNNs, and then we'll touch transformers. We have already spoken about a lot of this in the introduction, and this is just an extension of the introduction. See, CNNs are more important or more used for your visual inputs. Now what happens, let's suppose there is a picture here, okay, and there are some clouds on the top, and then there is a sun, and let's suppose there is a sea, and it's a very bad picture, but just bear with me. So in case of visual inputs, what happens that let's suppose we were talking about a pixel here. A pixel here, it has a very strong relationship with its immediate neighborhood pixels rather than some pixel here. Okay, so even when a human being looks at an image or looks at a painting, he also interprets most of the real life objects that the picture contains in a more regional perspective. So similarly, what we do is, let's suppose there is a picture which has a lot of pixels, and I'm just making a grid out of it so that it becomes easier for us to understand. And these grids can have values between say 0 to 255, because that's how our grayscales are defined. We create a kind of a convolutional window. Let's suppose we are getting a 3 by 3 window, and this kind of a grid we superimpose here. So if I superimpose this on the top left, I will superimpose this here. Okay, so now if I superimpose this window here, and this will have some numbers, and there is a assume that it has some number, some weights. Okay, now these weights, when they get superimposed here, I combine them. Let's suppose it's a simple cell-wise multiplication and addition. So let's suppose there is a value of say x11 here, and this is your w1, w2, w3, w4, so on and so forth. So I multiply x11, let's suppose this is x12, x13, x21, x22, x23, x31, and so on. So I will do x11 multiply by w1 plus x12 multiply by w2, and so on. So whatever I get in the final, that is something that I'm going to put in my new grid. Okay, so that's my final output. So I do this for each and every I will take this from the top left to the top right. When top right, I can only take this to this position, then there is no space, and then I create a different grid which is going to be smaller than this. How much smaller? It's going to be, let's suppose these are your n width, and let's suppose this is your k width. This is going to be your n minus k plus 1, right? So if this is 10 and this is 3, so you start from here and you eventually get till this place, so it's going to be 8. So that's what you do, and then you can do some kind of a pooling layer in between, which is some kind of an averages, and eventually you run this a couple of times, and then even see at the end of the day it is a neural network only, and then you use the fundamentals of artificial neural network, and then you train your classifier, whether it is to classify numbers or do anything else. So it has been found that some of the networks, there could be some famous networks that, let me see if they have spoken about some of these convolutional neural networks, or we would have already spoken about that in the introduction. But this is how this CNN operates. It creates this kind of a rolling window, and then finds your localized accumulation of localized weights and then creates new windows, and then you do pooling and convolutional time and again to reduce the dimensions and make your neural network more and more stronger. That's on the CNN. RNN is called a recurrent neural network, which used to be a very powerful. So it's generally used for more of a streaming kind of a input, which can be an audio stream, which can be a text stream, not for visual so much. And what happens at your time equal to t equal to say 1 and at time equal to t equal to 2, in addition to everything else, it also takes the output from your previous network to your current network. That's it. Okay, so that should be good enough. We don't want to get into the details of neural networks and then some other forms of neural networks like LSTM, etc., because we don't use them too often right now. What we use right now is something called as a autoencoders. Okay, and this is something that started with this famous paper, Attention is All You Need, in 2017, where you have, say, a set of inputs and you encode them. Okay, you encode them into some kind of an intermediary code, and then you expand this again to get your final output. So this side, which converges your input into this intermediary code, is called as encoder, and the other side, which does the opposite, it expands your intermediary code into your output, is called as a decoder. And hence sometimes these are also called as a sequence to sequence classifiers. There's a this a kind of a sequence here and a sequence there, so sequence to sequence classifiers. Now GARP will not get into the details of how this entire thing works, because if you read about the architecture of your autoencoders, it is very complex. There are nuances with respect to how the information is stored, how the information is maintained. The primary objective or the primary power of autoencoders is that it maintains your short-term and long-term context, or short-term and long-term memory. How it does is with the use of a variety of encodings, whether they are like positional encodings or they are encodings with respect to the particular keys that we are interested in, but we'll not get into those details. You just have to remember that it's a two-way process where your input is encoded into an intermediary code first, and then this intermediary code is converted back into a decoder. So important examples, let's suppose we are creating a language translator like our Google Translate, which let's suppose which translates English to Hindi or any other language for that matter. So it is going to consume English, create some kind of an intermediary code, and then convert it back into, say, Hindi. There are variants of transformers which can be, say, encoder only, and there it can be decoder only, and then there can be multiple encoders, multiple decoders, etc. Encoder only transformers means that they'll only do the first half of this part, which is and the examples can be in transformers like BERT, which converts your text into some kind of embeddings. And decoder only transformers are the very famous GPT and all of those transformers, where you only start from here and then you start decoding, more like your next token extraction. GPT is much beyond that. There are more steps, but there are decoder only, and then there are encoder decoder, which we already spoke, is about language translations. So that's about your transformers. I think that brings us to the end of this chapter. I have I have made this more precise. I have made this more on a high level, because if we get into more details or more analysis, it is anyway going to make it unnecessarily complicated for you. The intent is not to make you a mathematician or a data scientist. Next, we are going to start with semi-supervised, which is the chapter 5 of module 2. And my intent is that let's finish module 2 as soon as possible, without getting into too much of depth, and then we'll start with the other modules which speak more about the ethical issues and how can we manage ethical issues, plus the data governance, model validation, which is a very important part of RAI exam. So thank you, and see you in the next video.